Implicit differentiation. We've already studied how to find the equation of a tangent line or the rate of change of a function, but we've only worked with explicit equations. In this section, we're going to talk about implicit equations. Explicit functions are the ones where we have our dependent variable y written as a function of our independent variable x. So y will show up on the left-hand side of the equation, x will show up on the right-hand side of the equation, and they're completely separate. X and y never show up on the same side of the equal sign. They also never show up in the same terms. Implicit functions don't follow these same rules. With an implicit function, x and y can be on both sides of the equal sign, and they can also show up in the same term. With these types of equations, we can find a function of x that defines y, and we call that implicitly defined. So y is implicitly defined as a function of x. Here's an example of an implicit equation. We have x squared plus y squared equals 25, and I've got that graphed here. It's the equation of a circle centered at the origin with a radius of 5. And we can see that this equation, as it's written, does not pass the vertical line test. A vertical line will cross through our graph more than once, meaning this is not a well-defined function. We can find a solution to this equation by solving for y. Start off by subtracting x squared from both sides of our equation. This will eliminate equals 25 minus x squared. We'll take the square root of both sides and remember to take both plus and minus of our square roots. And this actually leaves us with two solutions. Y can be equal to the positive or negative square root of 25 minus x squared. If we just consider the positive square root, that'll give us the top half of the circle. If we only consider the negative square root, that'll give us the bottom half of the circle. We can also do a combination of the two with a piecewise function. So we can use the positive square root when x is greater than or equal to 0, and use the negative square root when x is less than 0. But this doesn't give us the full circle either. This would only give us 2/4 of the circle. So we see the gold curve in the first quadrant, the blue curve in the third quadrant. Or we can swap where the negative sign is. So instead of putting the negative on the x less than 0 definition, we can put the negative on the x greater than 0 definition. That would give us the other 2/4 of the circle. So we found multiple equations, multiple functions of x that solve this equation, and none of them actually give us the entire circle. We would need all 4 pieces together to make the full circle. Which means if I wanted to find the equation of a tangent line in quadrant 2, I would need to use the appropriate function of x to find the tangent line here. And if I wanted to find the equation of a tangent line in quadrant 1, I would need to use a different function of x to find the equation of the tangent line here. So using these explicit functions that solve our equation can be cumbersome because there's so many of them. The process of implicit differentiation can be summed up in 4 steps. First step is take the derivative of both sides of your equation. Second step, rewrite the equation so that you can isolate all of the dy dx terms. Sometimes you'll need to factor out your dy dx before you can solve for dy dx. Let's try an example. Working with that same equation of a circle that we had in the previous slide, I can take the derivative of both sides of my equation on the left side, we're actually taking two derivatives. One derivative of x squared, another derivative of y squared. On the right side of the equation, we're looking at the derivative of a constant, so we know that's equal to 0. The first derivative of x squared, that just becomes 2x, but this middle term, the derivative of y squared, that requires the chain rule, where y is the outside function, x is the inside function. Which means we're going to first take the derivative with respect to y, then we're going to take the derivative with respect to x of the variable y. The derivative of y squared with respect to y, that looks a lot like what we did over here with x squared. That becomes 2y, but then that's multiplied by dy dx. So when we take the derivative of this y squared term, it becomes 2y times dy dx. And I'll copy down that it's equal to 0. That's step 1 of implicit differentiation, taking the derivative of both sides of your equation. Step 2 is isolate the dy dx term. To do this, first we want to make sure we know where the dy dx terms appear. And then we want to move everything away from it. So we can start off by subtracting 2y, just kidding, subtracting 2x from both sides of the equation, which eliminates the x term on the left, leaving us with 2y dy dx is equal to negative 2x. And then lastly, to isolate that dy dx term, we need to divide by 2y on both sides of our equation, leaving us with dy dx equals negative 2x divided by 2y. We can simplify this dividing off the 2's, so we have negative x over y. So our final answer is that dy dx is equal to negative x divided by y. And we found this using the process of implicit differentiation.